In this video, we're going to look at some technology issues to consider when we're looking at the continuity of graphs that we've created using some sort of technological interface like a calculator or Desmos or something like that, even Excel. We want to be really careful with using graphs created by technology to evaluate continuity. And there's a few reasons for that. I'll show you a couple of examples. For one, when we've been looking at graphs in the textbook, for example, and we want to determine if graphs are continuous at a particular point, the textbook is really good at calling out issues where there's a hole in the graph, a sharp point, a skip, a break, a jump, something like that, right? We get all of that presented pretty well graphically in the textbook. The same cannot always be said for technology. So there's actually this box in your book, this technology tip, that says in some viewing windows, so depending on how you've set up your X and Y axes on your technology, a calculator graph may appear to have a sharp corner when in fact the graph is actually differentiable at that point. And then it says, when in doubt, try a different window to see if the corner disappears. And I can't remember if it actually gives us a visual example of that. Here's actually an example of one where a graph is not differentiable at a particular value, but from the graph provided, it looks like it might be. So there's one example of that. So sometimes, again, changing your window can make it much more obvious when something is and is not differentiable. And the only example that your book brings up is like the sharp corner, but I want to show you another example. And that is a function like this one. So here I'm using a graphing calculator app on my iPad. And you can actually do the same thing on a TI. You don't have to follow along, but if you wanted to, you could put this function in. So this is a rational function. It has x minus 2 in the numerator, and in the denominator, it has the quantities x minus 2 times x plus 3. Now, technically, this function is undefined at the x value of 2. Right? Because if we put 2 in, it would zero out that factor in the denominator. We would be dividing by 0. That leads to an undefined function. If we ask the calculator to graph this function and we use the standard window provided, we can see that there's this vertical asymptote of the graph at, let's see, that's at -3, which we would expect because of that factor of x plus 3 in the denominator. But we don't actually see anything weird going on at the x value of 2, even though the function is not defined there. And again, that's largely because of the window that we've chosen. If we zoom in, let's see, is it going to let me just, there we go. If we zoom in and start looking at the value of 2, well, that's interesting. When I graphed it earlier, it actually showed the hole there, and now it's not. Okay, so again, interesting limits of technology, right? We still can't see the hole at the value of 2. However, if I close this and I go to my table of values, let's say I want to start at 2 because that's where we expect the hole in the graph to be. And here I go. I can see the hole in the table of values, right? It shows me that at 2, I don't have a defined value for this function. So again, these are the kinds of things that we want to be careful about when we're using the graphs that are created by technology. When we're using the graphs that the textbook provides, they will usually call out any of those interesting features, but those features may or may not be visible on your technology depending on which type of technology program you're using, and even which format you're using. Like I said, here we couldn't see the whole on the graphical view, but we can see it in the table of values. So just be aware of that and use technology with caution.